Welcome to Universe Intelligence. Today we're diving deep into the fascinating world of prime numbers and grappling with one of mathematics' most challenging unsolved problems, the Riemann hypothesis. The Riemann hypothesis holds profound implications for our understanding of numbers and their distribution. Its solution could unlock secrets about the very fabric of our mathematical reality, with potential consequences for fields like cryptography and computer science. Get ready to explore the historical figures who laid the groundwork for this captivating problem, and delve into the complex mathematical concepts that underpin the Riemann hypothesis. By the end, you'll have a newfound appreciation for the beauty and power of mathematics. Let's start with the basics. What are prime numbers and why are they so important? A prime number is a whole number greater than 1 that can only be divided evenly by 1 in itself. Think of 2, 3, 5, 7, 11, and so on. They are the building blocks of all whole numbers. Just like atoms combine to create the vast diversity of matter we see around us, prime numbers can be multiplied together to form any other whole number. This fundamental property makes them essential to number theory, the branch of mathematics dedicated to exploring the properties of integers. While we know that there are infinitely many prime numbers, their distribution along the number line appears to be random and unpredictable. This seemingly chaotic arrangement has fascinated mathematicians for centuries, leading to numerous attempts to find patterns and predict where the next prime number might appear. This is where the Riemann hypothesis comes in. It offers a tantalizing clue about the hidden order within this apparent randomness. It's a bold conjecture that attempts to predict the distribution of prime numbers with remarkable accuracy. The story of prime numbers begins in antiquity, with mathematicians recognizing their unique properties even before they had formal mathematical systems to describe them. Ancient civilizations, driven by practical needs like dividing land and resources, likely encountered the concept of prime numbers organically. The ancient Egyptians, known for their advanced mathematics used in surveying and construction, likely had some understanding of prime numbers. Evidence suggests they grasped the concept of indivisibility, a key characteristic of primes. We have more concrete evidence of prime number exploration from the ancient Greeks. The Pythagoreans, a school of thought led by the famous mathematician Pythagoras, were particularly interested in the mystical and mathematical properties of numbers. Perhaps the most famous Greek contribution to our understanding of prime numbers comes from Euclid, who lived around 300 BC. In his monumental work, Euclid proved that there are infinitely many prime numbers. As mathematicians recognized the importance of prime numbers, they sought ways to identify and list them efficiently. One of the earliest and most ingenious methods for finding prime numbers is the sieve of Eratosthenes, named after the Greek polymath Eratosthenes, who lived around 200 BC. Imagine a grid containing all the natural numbers up to a certain limit. The sieve of Eratosthenes works by systematically eliminating multiples of each prime number, starting with 2. First, you cross out all multiples of 2, then all multiples of 3, then all multiples of 5, and so on. The numbers that remain uncrossed are the primes. The sieve of Eratosthenes, though simple in concept, provided a powerful tool for generating lists of prime numbers, and offered early insights into their distribution. Although the sieve of Eratosthenes is an effective method for finding smaller prime numbers, it becomes computationally expensive for larger numbers. This limitation fueled the ongoing search for more efficient algorithms and deeper understanding of prime number distribution. The study of prime numbers experienced a resurgence in the 17th century, with mathematicians like Pierre de Fermat and Marin Mersenne making significant contributions. Pierre de Fermat, a French lawyer and amateur mathematician, is best known for his notorious last theorem, which remained unproven for centuries. However, Fermat also made significant contributions to the study of prime numbers. He is particularly remembered for his little theorem, which provides a powerful tool for working with prime numbers and modular arithmetic. Marin Mersenne, a French priest and mathematician, focused his attention on a particular type of prime number that now bears his name, Mersenne primes. These primes, taking the form 2 to the power of p minus 1, where p is also a prime number, proved particularly intriguing to number theorists. Mersenn's work on these special primes sparked a quest for larger and larger prime numbers, a quest that continues to this day. As we move into the 18th and 19th centuries, mathematicians like Carl Friedrich Gauss and Adrien Marie Legendre made groundbreaking progress in understanding the distribution of prime numbers. Carl Friedrich Gauss, often hailed as the Prince of Mathematicians, displayed a keen interest in prime numbers from a young age. Through meticulous observation and calculation, Gauss developed the prime number theorem, a landmark result that describes the asymptotic distribution of prime numbers. Adrien Marie Legendre, a French mathematician, made significant contributions to various fields, including number theory. He independently formulated a version of the prime number theorem and made important advances in understanding the distribution of primes within specific arithmetic progressions. The work of Gauss and Legendre marked a turning point in the study of prime numbers. They moved beyond simply identifying and listing primes to developing powerful theoretical frameworks for understanding their distribution. Their work set the stage for Bernhard Riemann's groundbreaking hypothesis, which would further revolutionize the field and open up new avenues for exploration. In the mid-19th century, Bernhard Riemann, a German mathematician with a profound understanding of complex analysis, made a daring connection between the seemingly chaotic world of prime numbers and the elegant realm of complex functions. This connection, embodied in the now famous Riemann zeta function, lies at the heart of the Riemann hypothesis. The Riemann zeta function, denoted by the Greek letter zeta, might seem intimidating at first glance, but its beauty lies in its ability to bridge seemingly disparate areas of mathematics. For real numbers greater than 1, the zeta function is defined as an infinite sum. Zeta of s equals 1 over 1 to the power of s plus 1 over 2 to the power of s plus 1 over 3 to the power of s, and so on, where s represents a complex number. Riemann's genius was in realizing that this function, originally defined for a limited range of values, could be extended to encompass the entire complex plane, a two-dimensional space where numbers are represented in the form a plus bi, with I being the imaginary unit, the square root of -1. This extension, known as analytic continuation, revealed a fascinating landscape of values for the zeta function, with profound implications for prime numbers. Riemann's exploration of the zeta function led him to observe a peculiar pattern in the distribution of its zeros. He noticed that some zeros were located along a vertical line in the complex plane, with a real part equal to 1/2. This line, now known as the critical line, became central to his hypothesis. The Riemann hypothesis, in its essence, makes a bold claim about these zeros. It states that all non-trivial zeros of the Riemann zeta function lie on the critical line. In other words, if you were to plot all the points where the zeta function equals 0 on the complex plane, the non-trivial ones would all fall neatly on this single vertical line. The term non-trivial is important here because there are some zeros of the zeta function that occur at predictable negative even integers, like -2, -4, -6, and so on. These are known as the trivial zeros and are well understood. The Riemann hypothesis focuses on the remaining more mysterious zeros, asserting that they all have a real part of 1/2. This seemingly simple statement has profound implications for our understanding of prime numbers. To grasp the significance of the Riemann hypothesis, we need to delve deeper into the connection between the zeros of the zeta function and the distribution of prime numbers. This connection hinges on a remarkable mathematical concept known as the Euler product formula. The Euler product formula, named after the prolific Swiss mathematician Leonhard Euler, provides an alternative way to express the Riemann zeta function. It states that the zeta function can be written as an infinite product over all prime numbers. Zeta of s equals the product of 1 minus p to the power of -s, all raised to the power of -1. where p represents each prime number. This formula elegantly connects the zeta function, defined over all natural numbers, to a product that involves only prime numbers. The behavior of the zeta function, particularly its zeros, is therefore intimately linked to the distribution and properties of prime numbers. While the Riemann hypothesis is deeply rooted in abstract mathematics, there are ways to visualize its concepts and implications, offering a glimpse into the fascinating world of complex functions and prime number distribution. One way to visualize the Riemann hypothesis is to imagine a three-dimensional landscape representing the values of the Riemann zeta function. The complex plane forms the base of this landscape, with the height above each point representing the absolute value of the zeta function at that point. The zeros of the zeta function would correspond to points on this landscape where the surface dips down to touch the complex plane. The Riemann hypothesis, in this context, suggests that all the non-trivial valleys in this landscape lie along a single straight line, the critical line, running through the center of the plane. These visualizations, while simplifications of the complex mathematics involved, offer a tangible way to grasp the essence of the Riemann hypothesis and its potential implications for understanding the distribution of prime numbers. Since its formulation in 1859, the Riemann hypothesis has captivated mathematicians worldwide, sparking countless attempts to prove or disprove its validity. Despite over a century and a half of intense scrutiny and significant advancements in mathematics, the Riemann hypothesis remains one of the most challenging unsolved problems in mathematics. Numerous mathematicians have dedicated their careers to unraveling the mysteries of the Riemann hypothesis, exploring various approaches and developing new mathematical tools along the way. While a complete proof remains elusive, substantial progress has been made in understanding the problem and its connections to other areas of mathematics. One notable advancement is the verification of the first 10 trillion zeros of the Riemann zeta function, all of which lie on the critical line as predicted. The quest to unlock its secrets remains a testament to the power of human curiosity and our relentless pursuit of knowledge in the face of profound mystery. To truly grasp the depths of the Riemann hypothesis, we must venture into the fascinating world of complex analysis. This branch of mathematics extends our familiar understanding of numbers to encompass the realm of imaginary and complex numbers, unlocking a treasure trove of powerful tools and unexpected connections. Imagine a number line, stretching infinitely in both directions. This line represents the real numbers, encompassing all rational and irrational numbers we encounter in everyday life. Now picture a second number line, perpendicular to the first, intersecting at the point representing 0. This vertical line represents the imaginary numbers, multiples of the imaginary unit I, defined as the square root of -1. Together, these two lines form the complex plane, a two-dimensional space where points represent complex numbers. The Riemann zeta function, central to the Riemann hypothesis, is one such function that thrives in the realm of complex numbers. Its behavior in the complex plane, particularly the location of its zeros, holds the key to unlocking the mysteries of prime number distribution. Section 2. Analytic continuation. Extending the reach of functions. Analytic continuation extends a function's domain beyond its initial definition. It's like expanding a map into uncharted territory. The Riemann zeta function initially holds for complex numbers with a real part greater than 1. Analytic continuation extends it to the entire complex plane, except s equals 1. This extension preserves the function's essential properties. It ensures the zeta function remains smooth and well-behaved. This reveals a richer landscape, including the crucial zeros. Section 3. The prime number theorem, approaching infinity's secrets. The prime number theorem provides insight into the distribution of prime numbers. It describes the behavior of the prime counting function, px. As we move along the number line, prime numbers become less frequent. The theorem estimates how many primes are within a given range. P, x, is asymptotically equivalent to x over ln all x. As x approaches infinity, the ratio of p.x to ix over ln x approaches 1. The theorem showcases the power of analytic techniques in understanding primes. Section 4. The Riemann zeta function's functional equation, a symmetry unveiled. The Riemann zeta function has a functional equation, revealing a symmetry in the complex plane. This symmetry connects its values at s and 1s, crucial for understanding its behavior. It implies that zeros off the critical line reflect across it. Proving all zeros lie on the critical line is key to the Riemann hypothesis. Section 5. Modular forms and the Langlands program, connections across fields. The Riemann hypothesis reveals hidden connections in mathematics, linking modular forms and the Langlands program. Modular forms are complex functions with symmetry, central to the Langlands program. They remain unchanged under transformations in the upper half-plane. The Langlands program connects number theory, representation theory, and algebraic geometry. It suggests a link between modular forms and Galois representations. This connection could unlock new insights into mathematics. Section 6. Random matrix theory, finding order in chaos. Random matrix theory, initially developed for physics, is now a powerful tool for investigating the Riemann hypothesis. The zeros of the Riemann zeta function share similarities with eigenvalues of random matrices. Despite randomness, eigenvalues exhibit order. This link has led to collaborations between mathematicians and physicists. Random matrix theory offers new tools for investigating the Riemann hypothesis. A century of unsolved mystery, the challenge endures. Despite over a century of scrutiny, the Riemann hypothesis remains unsolved. It's one of the Clay Mathematics Institute's Millennium Prize problems, with a $1 million reward. The hypothesis captivates mathematicians for its implications on prime numbers. It stands as a testament to the limits of our knowledge. The challenge endures, inspiring new generations. Glimmers of progress, partial results, and supporting evidence. Significant progress has been made in understanding the Riemann hypothesis, with compelling numerical evidence supporting its validity. Powerful computers have verified the first 10 trillion zeros of the Riemann zeta function, all on the critical line. While impressive, this empirical evidence is not a mathematical proof. The Riemann hypothesis requires a rigorous proof for all non-trivial zeros. However, the numerical evidence motivates further investigation. Mathematicians have also made progress in related areas, offering hope for a solution. These connections provide alternative pathways for approaching the problem. The unexpected connections between the Riemann hypothesis and other fields are profound. These connections offer hope for a deeper understanding and potential solution. New avenues of exploration, interdisciplinary approaches, and emerging tools. The quest to solve the Riemann hypothesis has driven mathematicians to explore new frontiers and embrace interdisciplinary collaborations. Advances in computing power offer promising paths towards a potential solution. Computational number theory harnesses computers to tackle complex problems. Sophisticated algorithms help explore the zeta function and prime numbers. Connections between the Riemann hypothesis and other areas offer new perspectives. These connections suggest a solution might be found by understanding underlying structures. The future of prime numbers. Unlocking the secrets of distribution. The Riemann hypothesis will shape the future of prime number research and influence various branches of mathematics. Its resolution could have far-reaching consequences for cryptography, computer science, and physics. If proven true, it would provide a precise formula for predicting prime numbers. This would impact cryptography, enhancing data security. The quest to unlock prime numbers is a testament to human curiosity and our pursuit of knowledge. The Symphony of Primes. From the ancient Greeks to modern mathematicians, prime numbers have captivated minds for centuries. These simple numbers hold profound secrets. The Riemann hypothesis remains an unsolved enigma. Solving it would revolutionize our understanding of numbers and push the boundaries of our understanding of the universe. Join the quest for universe intelligence. As we conclude our exploration of the Riemann hypothesis, we stand at the precipice of the unknown, filled with a sense of wonder and a thirst for further discovery. The world of mathematics is vast and mysterious, with hidden connections and profound truths waiting to be uncovered. Universe Intelligence is dedicated to guiding you through this fascinating landscape, exploring the most intriguing concepts and unsolved mysteries in mathematics and beyond. We believe that understanding the universe begins with understanding the language it's written in: mathematics. Subscribe to Universe Intelligence and join a community of like-minded individuals who share a passion for knowledge and a desire to explore the universe's most captivating secrets. Together, we'll delve deeper into the world of mathematics, physics, computer science, and beyond, unraveling the mysteries that connect us all. Our journey through the world of prime numbers and the Riemann hypothesis is just the beginning. There are countless other mathematical wonders to explore, from the beauty of fractals to the complexities of chaos theory. Let Universe Intelligence be your guide as we continue to explore the elegant and awe-inspiring universe of mathematics.